Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book. I'm doing chapter 6 of volume 1, which is on group theory, discussing a lot of different kinds of groups. I'm doing subsection 6.2.2, which is on various types of permutation groups. And today I'm going to talk about odd and even permutations. It turns out that we can classify all permutations as either odd permutations or even permutations. I'm going to say what those are and give some examples. So anyway, let's begin. So what is an odd and an even permutation? Well, I talked about different representations of permutations. In particular, I talked about the cyclic representation. And it's easier just to think about cycles to begin with. Not every permutation is a cyclic permutation. But cyclic permutations can be represented as cycles. So, for instance, the way I've written it here, we have a cycle which I'm calling little c, which is in cyclic notation S1, S2 up to Sm. This would be a cycle of length m or of order m. So S1 goes to S2, S2 goes to S3, Sm minus 1 goes to Sm, and Sm goes back to S1. That's just a single cycle, which is a type of permutation. But one useful fact, I think I mentioned this yesterday, one really useful fact about permutations is that every permutation can be written as a product of transpositions. And transpositions are the simplest non-trivial type of permutations. They're just permutations that swap two elements of your set. They have order 2. If you like, they're cycles of order 2. So the way you can write an arbitrary cycle, it turns out, is a product of transpositions. You can write this cycle I just wrote down above as the product of S1, S2, that's your first transposition, and S2, S3, that's your second, S3, S4, so on, all the way up to Sm minus 1, Sm. It turns out that that product is the cycle I wrote down earlier. It's a cycle of order m. And notice that there are m minus 1 transpositions in this product. So, for instance, if m is odd, that means that there's an even number of transpositions. We would call that an even permutation. And if m is even, then there'd be an odd number, m minus 1, and would be odd, so that we would call it an odd permutation. That's a little bit confusing because it turns out that cycles of even order are odd permutations and vice versa, cycles of odd order or even permutations. You might think this is not a well-defined concept because it turns out that the representation of, I'm just talking about cycles here, by the way. And remember that every permutation can be written as a product of disjoint cycles. So you can write each cycle as a product of transpositions. And since you can do this for every cycle in your cyclic representation of your permutation, that means you can write the whole permutation as a product of transpositions. So that means that every permutation is a product of a finite number of transpositions. And it turns out, no matter how you write that, that's not a unique representation. There's a lot of different ways you can represent a given permutation as a product of transpositions. But one interesting fact, which I'm not going to prove, but it's true, you'll have to take my word for it, is that the parity of the number of transpositions is constant. And so they're different representations as a product of transpositions of a given permutation, but the parity, the number of transpositions is always they're all either all odd or they're all even. And if they're all even, we call it an even permutation. If they're all odd, we call it an odd permutation. So that's the definitions of odd and even permutations. I know that's kind of a lot to grasp, but yeah, I guess I already said at the beginning of this slide. Yeah, so, and then, a useful fact, what happens when you multiply two permutations? For instance, what would happen if you multiply two even permutations? Well, if remember that even permutation is one where you can write it as a product of an even number of transpositions. So if you have two of them, You got even plus even, that's even. So the product, that means the product of two even permutations is an even permutation. What about the product of two odd permutations? Well, if they both are odd permutations, that means they're both represented as an odd number of the product of an odd number of transpositions, and when you multiply them together, the total number of transpositions is odd plus odd even. So that means that the product of two odd permutations is also even. And what about an odd and an even permutation? Well, I think you kind of get the idea. Your first permutation is odd, and your second permutation is even, or vice versa. The total number of permutations is going to be odd, because odd plus even is odd. So that means that either an odd permutation multiplied by an even permutation, or the other way around. Even permutation times odd permutation. Those are both odd. So that's how permutations multiply in terms of their parity, which is a nice fact. Yeah, now I'm just going to do a couple examples because this is a lot to take in. So for first example, this is a pretty easy example. We have the permutation, which in the cyclic representation we can write as the product of 1, 2, 3, the cycle 1, 2, 3, and the cycle, and the transposition 4, 5. So we want to know whether this is an even or an odd permutation. Well, 1, 2, 3, like I said, that's a cycle of odd order. That means it's an even permutation. If you like, it's either 1, 2 times 2, 3. It's just the product of those two transpositions. So that's even, but then 4, 5 is odd. Single part transposition is an odd permutation. So you're going to have a total of 3 transpositions, in this product. 3 is odd, so that's obviously an odd permutation. Let's do another example. This one's a little harder. Here I wrote it out in permutation representation. So this is the permutation of a set of orders of cardinality 7, A, B, C, D, E, F, G. And this particular permutation sends A to B, B to A, C to E, D to F, E to G, F to D, and G to C. So now we want to know whether this permutation is even or odd. Well, it's better to try to write it in a cyclic representation, so we just trace what happens to every element. So A goes to B and then B goes back to A. That means that the transposition AB is part of the cyclic representation. And then we see what happens to C. C goes to E, E goes to G, G goes back to C. So that's going to be a cycle of order 3. That's going to be the cycle CEG. And then finally, D goes to F and F goes to D. That's another transposition. So when we write it out in the cyclic representation, we have AB, transposition AB, times 3 cycles CEG, and transposition DF. Well, we got 2 transpositions and a 3 cycle, and we know transpositions are even permutations, or odd permutations. We have 2 of them. So the product's going to be even, and also the 3 cycle CEG, that's a cycle of odd length. That means that's also an even permutation. So we have everything's even. And so this means that P is an even permutation. So that's how you determine whether permutations are even or odd. And this is going to turn out to be a very useful property in permutations. It turns out, I'm just going to jump the gun a little bit here. It turns out that the subgroup of even permutations of the symmetric group is a group. I said subgroup, so I sort of led into that. It turns out the set of all even permutations of any finite set is a group. Actually, another interesting fact. I'm jumping on a little bit more here. It turns out that every as long as your set has cardinality 3 or larger, exactly there's the same number of even permutations as odd permutations. Exactly half of them are even, and the other half are odd. So anyway, that completes my video for today on odd and even permutations. Thank you for watching. Long live math, and I'll see you guys next time. Bye.